Welcome back. So we were talking about CNN, deep learning models, and now hopefully we have a better understanding of what convolution is and why we use it in the context of neural networks. So here in this short lecture, I just want to talk about some examples of CNN architectures and also see why we may need to also incorporate another modification in this kind of architectures. All right. So the first model I want to talk a little bit about is the perhaps the first example of a CNN model, and that's called LeNet. It's named after Professor Yuval Nikol, one of the influential figure in deep learning and machine learning. So this model is built to classify images for a dataset that's called MNIST. That's a dataset of grayscale images of 28 by 28 pixels about digits, right? So digits from 0 to 9, right? So, and the goal is to classify these images. So the network has a bunch of layers. So we have basically a convolution layer, we have a pooling layer. Again, this is followed by a convolution and a pooling layer. Finally, we have a number of dense layers. So these are basically the multi-layer perceptron that we talked about. And finally, the output is basically a layer with 10 neurons. So this is to say that we are basically dealing with a classification problem with 10 classes, right? And the output, again, the dimension is 28 by 28 because we have an image of size 28 by 28. Okay, so the next model is called AlexNet. That was proposed in 2012. And this is another example of a CNN model, but it's built to sort of tackle a different data set, the ImageNet dataset. There we have RGB images, so our object is essentially three-dimensional. So the number of channels is 3, and each image is of size 224 by 224. So that's the total number of pixels, and we have 1,000 classes. Okay, so what's AlexNet? Again, it performs CNN, so convolutional filters with max pooling. So we have a strider 4 here. And as you can see, we gradually reduce the size of the image as we progress. So we have the first CNN layer is followed by max pooling. Again, CNN, max pooling, and we repeat this process. And finally, we implement a couple of dense layers, and then we have the output layers. Okay, so most of these models are a combination of CNNs and dense models, as well as the pooling operation and striding and padding that we talked about. All right, so designing new architectures is going to be cumbersome. So one design principle is the blocks and modularity. So it is therefore desirable to have to design blocks that we can repeat and build deeper and deeper neural networks. So here I'm providing two examples that follow this principle. The first one is called the VGG16 model. This is again a model that's designed to tackle the ImageNet dataset. So here, as you can see, we have a bunch of blocks that are a combination of convolution and max pooling, and then we repeat these blocks. Okay, so this is called let's say first block, second block, and again we have another block of again a slightly different block, but still it includes convolution layers with the ReLU activation as well as max pooling. We repeat it a couple of more times, and then we follow these convolution layers with fully connected layers and build the output layer. Again, the output layer is 1,000 dimensional because we have a classification problem with 1,000 classes. Okay, and the next model is called ResNet 18, and again you can see that we have blocks and the model sort of repeats this block a couple of times in this architecture. Okay, but there are some new concepts here. So there is one block or like one operation that's called batch normalization. We will talk about this in the next lectures. But the point that I want to make here is that compared to all the previous architectures where there was only a single path from the input to the output, so the information could only flow from this single path, here in ResNet, that's not the case. We have these, if you will, skip connections. So one skip connection here, another one here, another one here, right? So that provides multiple paths for the input to go from the input layer to the output layer. And this is shown to be quite an influential change to make to enable building deeper and deeper neural networks that can potentially perform better than the existing models at the time. Okay, so I want to talk a little bit about the importance of the skip connection. All right, so the idea is based on some empirical observation we've had when training shallow neural networks and deep neural networks. Okay, so and the empirical observation that we had is that we expect the deep networks to perform better than the shallow ones in terms of both training and test error. And this is indeed an observation that we've made. So here, as you can see, there is this gap between the final performance of a shallow neural network and a deep neural network. However, what we have observed is that early on in the training process, the shallow network can make progress faster than a deep network. Okay. Now, this could be attributed to the fact that we typically initialize the models at random, and this is something we're going to talk about in the future lectures. Now, one implication of random initialization is that early on in the training, when we have we are processing an input, and again, the input is going to provide useful information for us to learn patterns from the data. The input gets multiplied by, let's say, these weights. The weights are random, and as the model gets deeper and deeper, we are multiplying the original informative signal with a lot of random quantities. So intuitively, as the data is processed, the kind of the signal that we see towards the end of the network is highly noisy and highly random, and it may not have an adequate correlation with the original input or original features. Okay, so therefore, this might mean that we're not going to be able to make progress fast early on because the weights are random. We don't have like a very strong signal early on. But as the model is updated and as the weights are moving away from random weights and essentially are optimized to learn the pattern from data, then we expect that, again, the final signal at the output layer has high correlation with the input. And also, given that our model is deep, we have a very high learning capability. Therefore, we'll be able to not only fit the data well, but also identify generalizable patterns and therefore improve the test performance as well. Okay. Now, the idea behind residual connections or a skip connection is to make sure we can carry out information over from the input side to the output side while still enjoying the high capacity of deep neural networks, right? So we want to make sure that we are building these skip connections such that the input, the informative signal, has another path to find its way back to the output, okay? And a similar statement could also be made for the gradient, because typically, as we're going to talk about, the gradient is calculated using the backpropagation algorithm. So not only we process the information in a forward direction, we also process it in a backward direction. So early on in the training, to calculate the gradient, we have to process, let's say, some data from in the backward direction. Again, we are multiplying quantities with noise, with a lot of noisy quantities, and therefore the early learning signal in the form of the gradient is not going to be as informative for deep networks that don't have a skip connection. All right. So ResNet architecture is basically constructed as a modular connection of residual blocks. So here I'm showing the residual connection. So these are the skip connection or the residual connection, and each of these is basically one residual block. So on the left-hand side, I'm showing two versions of a residual block. One version, you basically directly connect the input to the output of the block, and then you perform, let's say, some concatenation. Okay. On the other hand, you may optionally perform a convolution operation before concatenating the input to the output of the residual block. Okay. Now, why the name? Why this particular name? And the name comes from the fact that the model is trying to learn the residual, basically the difference between the input and output of a residual block. So, and this is different than the feed-forward neural networks without any skip connections, where we essentially are trying to learn the relationships or the label rule that characterizes the relation between the input and the output. Okay, so the idea is that learning the residual could be simpler. Why? Because the ideal residual is small. So learning a small quantities is intuitively easier than learning large quantities. Okay? So therefore, by adding this skip connection, we may be able to improve the learning capability of the model. Okay? Now, this another important point to make here is that this skip connection is actually used not only in construction of residual networks, but also other architectures, for instance, transformers, that are perhaps one of the most famous architectures these days, that are basically the building block of all of these large language models that we may have some experiences dealing with them and interacting with them. Now, there is also another intuitive explanation of why residual connection could be helpful in terms of not only accelerating the learning, but also improving the test and training accuracy. The idea is that this modularity in residual networks leads to a nested capacity. So as we are adding more and more to the depths of the network, we are guaranteed to enlarge the capacity of the network in a way that the deeper network is guaranteed to be always better than the smaller network. So essentially, without skip connections, or if you are talking about a non-nested function class, as we are increasing the depths of the network, we again intuitively expect the capacity to increase, but it's not guaranteed that the best model inside a large class is going to have, let's say, the best performance compared to a smaller class. For instance, let's consider this larger neural network. So this you can imagine to represent, for instance, all MLPs with 10 layers. Okay. Now let's say that if I were to optimize it, I would find a function here. So this would be, let's say, my optimal model. On the other hand, if I consider a smaller MLP architecture, let's say MLPs with 5 layers, when optimizing, I'm going to, let's say, find a model here. Now let's imagine that the true label law is this star point, right? So it could be that the optimal 5-layer MLP is going to perform better than the optimal, and by optimal I mean the solution to the empirical risk minimization problem, the optimal 10-layer MLP. Okay. However, when we are adding these skip connections and building a residual neural network based on these residual blocks, we are sort of ensuring that we have this nested function class. Therefore, if let's say the best model is so therefore, as we are increasing the depth of a model, we are increasing the capacity, but also we are making sure that the optimal deeper model is going to perform better than the optimal shallower model, okay, as demonstrated in the figure on the right-hand side. All right. Now, one other nice thing about the residual networks is that they have a very immediate connection to differential equations. Okay, so let's consider an ordinary differential equation. Essentially, the derivative of x with respect to, let's say, time is some function of x and time. Okay. Now, one simple approach to solve these kind of differential equations is the Euler method. Essentially, we'll discretize the equation and try to find the solution in an iterative approach, using an iterative approach. Okay. So the idea is therefore that we're going to form the following update. Xt plus 1 is xt. So this difference is essentially the discretization of the derivative plus f at t and xt. Okay. Now, if we do some rearranging, you'll notice that this difference is essentially, again, like the residual, is equal to f at t and xt. Okay. So therefore, we see this connection here that the f is basically our residual. So in ResNet, we are trying to learn the residual. So therefore, we can leverage residual networks for solving and discovering governing equations described by, let's say, differential equations. Okay. So therefore, residual networks have been shown to be very useful in solving and modeling ODEs, as well as other physical governing equations. Now, this area is an active area of research, which is called the physics-informed deep learning or machine learning. And the idea is that when we want to use these data-driven approaches for physical data, we can leverage some side knowledge to perform without having access to a large number of data sets or a large data set. And the idea is that in a lot of scientific applications and scientific discovery applications, we don't have access to large data sets as we do in other domains such as computer vision and natural language processing. Therefore, we have to compensate this lack of data by leveraging side information and, let's say, the physics behind the problem that we are tackling. So therefore, this is a very brief overview of some of the famous convolutional neural networks, notably residual network. In the next lecture, we're going to talk about a different kind of architectures, namely recurrent neural networks that are designed to deal with data of sequences. I'll see you next time.